Hi students, welcome to my channel. In this video, we are going to learn the basic expression for Coulomb's law and discuss important aspects of Coulomb's law. Consider two stationary point charges in vacuum or free space. That is, in vacuum media, we consider two point charges and they both are at rest and separated by a distance r. Students, you all know that point charges are infinitesimal, that is, they are not zero in size, have neither area nor volume. The charge it possesses is considered to be concentrated at a single point. Okay, I will repeat here. The point charges are infinitesimal. They have neither area nor volume and the charge it possesses is considered to be concentrated at a single point. In the year 1786, an scientist named Coulomb deduced the expression for force between two stationary point charges in vacuum or free space. Let us consider charges Q1 and Q2 be two positive point charges and separated by a distance r. If the two charges are like charges, the force will be repulsive, and if the two charges are unlike charges, the force will be attractive. Here we consider two positive charges, so that force is repulsive and two, the field lines point away. Coulomb deduced the expression for force as F is proportional to Q1 Q2 by R square. Now we are going to learn the important aspects of this expression, that is the importance of each and every variable used in this expression. The important aspects which are to be discussed in Coulomb's law are the statement of Coulomb's law, vector representation of Coulomb's law, proportionality constant K and permittivity of free space epsilon naught, magnitude of electrostatic force, relative permittivity epsilon r, comparing Coulomb's law and gravitational law, comparing Coulomb's law and Newton's third law, and limitations of Coulomb's law. Okay, students, now let us discuss one by one. First aspect is statement of Coulomb's law. The Coulomb's law states that the force of attraction or repulsion acting along a straight line between two electric charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. From the expression, we see that F is inversely proportional to R square. That is, lesser the distance between the point charges, greater the attractive or repulsive force. And 2, greater the distance between the point charges, lesser the attractive or repulsive force. Okay, now we move on to the second aspect. The second aspect is vector representation of Coulomb's law. Here we consider positive point charges. So, force acting will be repulsive. Now, the force acting on charge Q2 due to charge Q1 is represented as F21 vector, that is on charge 2 by charge 1. Then the force acting on charge Q1 due to Q2 is F12 vector, that is on charge 1 by charge 2. Therefore, the forces acting on the charges always lies along the line joining the two charges. For the force F21 vector, that is force on charge Q2 due to Q1, the distance is written as R12 vector, indicating the direction from charge 1 to charge 2. Similarly, for the force F12 vector, that is the force on charge Q1 due to Q2, the distance is written as R21 vector, indicating the direction from charge 2 to charge 1. Okay, now we are going to introduce unit vectors to represent direction. You all know that unit vectors have magnitude equal to 1 and indicate direction. Any vector divided by magnitude gives unit vector, isn't it? A vector possesses both magnitude and direction. If we divide by magnitude, we get direction. That is, R unit is equal to R vector by R magnitude. Okay, now we are going to write R12 vector and R21 vector in terms of unit vectors. For F21 vector, R12 vector is written as R12 vector is equal to magnitude of R12 into R12 unit vector. For F12 vector, R21 vector is equal to magnitude of R21 into R21 unit vector. Now, Coulomb's law in vector representation is given by F21 vector is proportional to Q1 Q2 by R12 square into R12 unit vector. Okay, now let us move on to the third aspect. The third aspect is proportionality constant K and permittivity of free space epsilon naught. On removing the proportionality sign, we introduce the proportionality constant K. In SI units, K is equal to 1 by 4 pi epsilon naught, that is equal to 9 into 10 power 9 Newton meter square C power minus 2. Here epsilon naught is the permittivity of free space or vacuum and epsilon naught is equal to 1 by 4 pi k, that is equal to 8.85 into 10 power minus 2 n power minus 1 m power minus 2 and c square. Now let us move on to the fourth aspect. Fourth aspect we are going to learn is magnitude of electrostatic force. Magnitude of electrostatic force F mod we are going to find. Let us assume Q1 is equal to Q2 is equal to 1 Coulomb and give the value of R to be 1 meter. Okay, the charges are of 1 Coulomb and distance is of 1 meter. Now F mod is equal to K Q1 Q2 by R square. You give the values 9 into 10 power 9 into 1 by 1 square. What we get is 9 into 10 power 9 Newton. This value is very large and we never come across 1 Coulomb of charge in our day-to-day life. We come across coulombs in terms of microcoulombs 10 power 6 C or nanocoulombs 10 power minus 9 C. Now let us move on to the fifth aspect. The fifth aspect we are going to learn is relative permittivity epsilon R. By Coulomb's law, the force between 2 point charges in vacuum is given by F21 vector is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square R12 unit. If we change the medium that is other than vacuum, what happens is the force between the 2 point charges will be F21 vector is equal to 1 by 4 pi epsilon m. We are changing the medium now, so epsilon m into Q1 Q2 by R square into R12 unit. The value of epsilon m is greater than the value of epsilon naught. So, what happens to the force F21 in any other medium is less than F21 in vacuum. The relative permittivity of a given medium epsilon r is epsilon r is equal to ratio of permittivity of medium to the permittivity of vacuum. That is epsilon r is equal to epsilon m by epsilon naught. For vacuum or air, we know that epsilon r is equal to 1. For any other medium, it is. Now we move on to the sixth aspect. The sixth aspect we are going to learn is comparing the Coulomb's law with gravitational law. We know the expression for Coulomb's law is F is proportional to Q1 Q2 by R square. Similarly, for gravitational law, G is proportional to M1 M2 by R square. This is a very familiar expression. And two, in the Coulomb's law, the charges can be either attractive or repulsive. It depends on the nature of the charges. But in gravitational law, there is always attraction between them. The value of Coulomb's constant is K is equal to 9 into 10 power 9 n m square c power minus 2, and the gravitational constant G is equal to 6.67 into 10 power minus 11 n m square kg minus 2. The electrostatic force between the two charges depends on the nature of the medium in which the two charges are kept at rest. But in gravitational force, the gravitational force between two masses is independent of the medium. Okay, now let us move on to the seventh aspect. The seventh aspect we are going to learn is Coulomb's law obeying Newton's third law. The force on charge Q1 due to Q2 is given by F12 vector is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square into R21 unit. We know that R21 unit is equal to minus R12 unit because they are of same distance but only opposite in direction. Now, in the place of R12 unit, we write as minus R12 unit. Then what happens to the force F12 vector is equal to minus 1 by 4 pi epsilon naught Q1 Q2 by R square R12 unit. And now F12 vector is equal to minus F21 vector. That is equal and opposite. Coulomb's force are equal in magnitude and opposite in direction. The forces exerted by the two stationary point charges on each other are always equal and opposite. Now, the eighth aspect we are going to discuss is the limitations of Coulomb's law. The Coulomb's law is applicable only for stationary point charges. If the charges are of arbitrary size, that is if they are not any specific size, Coulomb's law cannot be implemented. And Coulomb's law can be applied when the sizes of the charges are very much smaller than the distance between them. And so the point charges are considered in Coulomb's law. Okay students, so far we have discussed the important aspects of Coulomb's law. Students, in the last part of this video, we are going to learn about Coulomb torsion balance. Coulomb torsion balance is the experiment developed by Coulomb. In this experiment, he considered charged spheres as point charges. The arrangements are in such a way that the distance between the two charged spheres are much greater than the radii of the spheres. He measured the electrostatic force between two charged objects and confirmed that it depends on product of the charges and inverse square of the distance between the two charged objects. Okay students, I believe that you all listened and learned. Now it's your task time. Take your note and recollect the points. It will be very useful for your studies. Thank you.